Right. So in the previous session we have seen about working of voltmeter, ammeter, current sources, voltage source, power source, and these network theorems. So now we'll see how to implement it in TINA. Okay. So for the constant current source, internal resistance is very high. So we're taking a constant power supply and we're adding very high resistance in series. Okay, so I take it as 1 mega ohm. Otherwise, you can edit the properties of this voltage source and add the internal resistance. You can add it in series externally, or you can edit these properties of this voltage source and add it internally. Both are possible. And then this load resistance, and we will see for what values of load resistance this current remains constant. Okay, that is the aim. So for lower values of resistances it is okay, but when resistance value approaches the value of internal resistance, this current reduces. I mean, if you plot a graph for RL, load resistance value versus current through it. For all smaller values of load resistance, current remains constant, and when it approaches the value of internal resistance 1 mega ohm, current starts reducing. So that is what we can observe in this. I mean, we have to add an ammeter in series to measure the current through the load resistance. Okay, so we'll be starting from 1 ohm, 10 ohm, 100 ohms, 1 kilo, 10 kilo, 100 kilo, 1 mega, 10 mega, and 100 mega. These are the values we are taking for load resistance. And if you plot a graph, it's around 10 kilo. This current starts falling down. That means if the load resistance value, even if it is 1000 times lower than the internal resistance, means starting from 10 kilo, sorry, 100 times, probably 100 times. So starting from 10 kilo, your current starts reducing. Okay, that is what we will observe in this constant current source. So the comparative parameter is 10 square. So if the load resistance, if the load resistance value is fixed, we must ensure that internal resistance should be at least 100 times more than the load resistance to keep the current value constant. Okay, so that is one. Another one is constant voltage source. So here internal resistance of voltage source is very minimal, near to 0. So I am considering 10 ohms as the internal resistance. So either you can add it in series or you can edit the internal properties of this voltage source. Both are possible. So I am showing it for the convenience outside. And we are adding a load resistance and measuring voltage across it. So internal resistance is when the load resistance is comparable to the internal resistance, this value, what happens? So the voltage will be very low, lower than the voltage supplied by the voltage source. So when the load resistance value increases enormously, the majority of the voltage will be dropped here, because this number is very small. Voltage drop will be negligibly small. So if you take this 10 ohms here, maybe after 100 times more than that, maybe after 1k, this value will remain constant. So at least the load resistance value should be 100 times more than the internal resistance of the supply. Right, and here also we are plotting a graph between RL versus voltage across load resistance. and I am taking values for load resistance starting from 1 to 10, then 100 ohms, 1 kilo, 10 kilo, 100 kilo, 1 mega, 10 mega and 100 mega, 100 mega ohms. So since this load resistance value is varying in the powers of 10, it is more convenient to represent logarithm of RL along x-axis, because the variations are in the powers of 10. Okay, so these two can be verified on TM. Right, so our next experiment is Thevenine theorem. The statement says any complex circuit can be reduced to a voltage source in series with a resistor. Right? So I am taking some complex circuit with resistors. This is a load resistance, this is a voltage R1, R2, R3. So this can be reduced to a constant voltage source in series with a resistance. Where that VTH is VTH is the open circuit voltage obtained by removing the load resistance. So we have to connect a voltmeter by removing the resistance here and measure the voltage. So this is R1, R2 and R3. So this value is VTH. So here you have to remove the load resistance and measure the voltage across the open ends. So when you are measuring the voltage across the open ends, so what happens? The internal resistance of voltmeter is infinity. Ideally, internal resistance is infinity. So this portion becomes a open circuit. So no current flows through R3, and entire current flows only through this channel R1 and R2, and ultimately VTH will be equal to voltage across R2. It is equal to VR2, which can be written as V times R2 by R1 plus R2. So that is VTH, and RTH is obtained by replacing the voltage source with its internal resistance. So internal resistance of voltage source is 0, so we have to replace this voltage source with its internal resistance, 0 value of resistance. So here R is 0. So since you are measuring resistance, we have to take resistance only for whatever component in the circuit. So I am replacing the voltage source with the internal resistance of voltage source. And so when you connect a ohm meter here, this is R1, R2, R3. This is RTH. So RTH value is given by R3 plus R1 R2 by R1 plus R2. So we have to construct all these 4 circuits and verify Thevenine theorem. So to repeat the experiment, which one should we take as a variable? R1, R2, R3, RL and V. And these are the equations involved. So which is more suggestible to take as a variable? Yeah, either R1 or R2. I mean R1 R2 are common in both of these two equations. So I prefer to take R2 as a variable. So how to do this now? So once you fix this VTH and RTH, what should we measure? Voltage through RL. Voltage across RL. So what is VRL? From this equation, VRL is, so VTH RL by RTH plus RL. So this is the ultimate confirmation for our calculations. So we have to calculate and get this value. At the same time, we have to measure the value and confirm it. So what all do we need to take as input? So other things like V, some value, R1, some value, R3, some value. These are the variables. RL is also a constant. I'm taking all those things as constants. Let's say take everything as 1 kilo ohm. And the variable is R2. So use Excel to prepare this table first. R2 value starts from 1 kilo, 2 kilo, 3 kilo up to 10 kilo. So once you know the value of R2, these are all already fixed. So VTH can be calculated using this equation. So R2 is a variable, R1 is fixed already, R2 is a variable. Next one, RTH can be calculated using this equation. So VTH comes here, RTH comes here. Next one, VRL calculated. So this is the value you will be calculating. Next one, the values that we measure. So the same thing, VTH measured, RTH measured, VRL measured. So once you construct these circuits and vary the value of R2, you can get that. So these three things come from Excel and these three things from your circuit. Okay? So ultimately you have to compare all your results with the voltage across RL in the original circuit. So VRL calculated, and maybe one more thing, VRL from original circuit. VRL from original circuit, VRL from equivalent circuit, Thevenine equivalent. So here V is 10 volts. Right, so the next one is Norton theorem. So here we will be reducing the circuit, whatever, any complex circuit can be reduced to a constant current source in parallel with a resistance. This can be reduced to a constant current source in parallel with the resistor. So here IN is the current measured by removing load resistance. So I have to measure the current here by removing the load resistance. This is R1, R2. I have to place an ammeter here instead of voltmeter. So since this is a ammeter, circuit closes. So in the case of Thevenine theorem, we have used voltmeter here. So internal resistance of voltmeter is infinity, circuit opens. So this part can be neglected in that case. Here ammeter internal resistance is 0. So it is a straight connection. So we need to measure the current flowing through this portion of the circuit. Okay. So we have to measure this current. So we have to remove the portion of the current divided here. Okay. So what is the entire circuit? R1, R2, R3, and we need this current. Okay. So now we have to see the current when this is a series circuit. Convert this into series circuit. This is R1, this is R2, R3 by R2 plus R3. So then we can measure the current through that. So what is the current through this? V equal to IR. I is equal to V by R. So V by R1 plus R2 R3 by R2 plus R3. So that is the current through this entire loop. So now this current is divided between these two. The same current is divided between R2 and R3, and what we need is the current through R3. So how to get that? I R3 is given by total current multiplied by R2, R2 plus R3. We have to use the opposite resistance. So I R3 is given by I R2 by R2 plus R3. I value is this. So I mean, you don't need to worry or you don't need to substitute all those numbers. You can just keep that. So I value is this V by R1 plus R2 R3 by R2 plus R3. I mean, you even can simplify and verify if you need, if you want. So what is this value? So V by R1 R2 plus R2 R3 plus R3 R1. multiplied by R2 plus R3. So if you substitute that, this becomes VR2 by R1 R2 plus R2 R3 plus R3 R1. That is current through R3. That is the value of IN. Right. So IN is given by VR2 by R1 R2 plus R2 R3 plus R3 R1. Rn is what is Rn? You have to replace the circuit values, power sources with its internal resistance. R1, R2, R3. So Rn is the same value, R3 plus R1, R2 by R1 plus R2. Okay. So you got the value of IL, Rn, RL, and finally you have to measure the current through RL. IRL is the final calculation. What is IRL? So it is a IN multiplied by Rn plus RL. You have to use the opposite resistance. So IN Rn by Rn plus RL. Because at that point current divides into two portions and you have to use the other resistance to measure the current through the given resistance. So what do you get? IN is, you don't need to simplify it, you can keep it. And if you want to know the value, and what about this? From here IRL is it is the same resistance that we are going to get here, but instead of R3 you have R3 plus RL. So instead of R3 you have R3 plus RL. So it is I R2 by R2 plus R3 plus RL. So this is one value that you are going to calculate. This is another value you are going to calculate. So what is the table? The same R2 is a variable here. So once you vary R2, you should get corresponding I. From there I R3, then Rn, then IRL, IRL equivalent, IRL original. These are the values you are going to calculate, and same thing you are going to measure. What are the things you are measuring? IR3 itself is IN, right? Okay. So IN measured, RN measured, IRL measured. is what you have to do. So these are all the calculated values on Excel. These are the measured values. IRL can be obtained from two circuits, this one and this one. Okay. So right. So next one is maximum power transfer theorem. Okay. So this theorem says when the internal resistance of the circuit is equal to load resistance, maximum power will be transferred to the load. Okay, so if Ri is equal to RL, maximum power transfers to load resistance. This is the statement. So now, which one should we take as a variable? What is the variable? Yeah. Ri or RL? So Ri is the variable. If Ri is equal to RL, so that is why I am fixing the value of RL, let's say 10K, and I am starting with Ri, let's say Ri, and power transferred to the resistor PRL. So when Ri is equal to RL, power will be maximum. So this is what we need to verify. Okay. So what is that we need to do? We have to calculate power through RL. So for that we have to get the value of current and voltage across RL and current through RL. So here VRL is what? VRL by Ri plus RL. This is the voltage drop across RL, and IRL, current through RL. So these two are in series. So it is V by R. So V by Ri plus RL is IRL. So in total PRL is power through RL. PRL into IRL is what? So V times RL by, so V square RL by Ri plus RL whole square. V square RL by Ri plus RL whole square. So that is the power. The most important problem with this is if you see the efficiency of the circuit, efficiency will be maximum when internal resistance is very high. So if you see the efficiency versus as a function of Ri efficiency, this graph continuously rises. So whatever maximum power point is not the best efficient point. That can be verified in this experiment. Okay, we'll calculate that efficiency also. Efficiency is what? P in by PRL. Sorry, PRL by P in. Output power by input power. So it is PRL by P in. So what is P in? Input power is what? Voltage multiplied by current. So PRL is V square RL by RI plus RL whole square by P in is voltage multiplied by current. Current produced by this battery is what? This is current. V by RI plus RL. So in total this is V square RL by RI plus RL whole square by V square by RI plus RL. So it is, efficiency is what? RL by RI plus RL. And here R is a variable. So confirm this, whether it is falling or rising curve. What do you get? Efficiency as a function of Ri. You need to confirm that, either this one or this one. So the table is what? Here Ri is the variable. Calculations VRL, IRL, PRL, measurements, eta is also calculated, and then measurement, PRL measured. Power reached by power here. Here V is 10, R is 10. So this theorem says, when let's say these two are resistors, let's say Ri and RL, okay, when both the channels are of equal width, means when both the channels, both the resistors are equal, let's say consider them as water pipelines. When both pipelines are of same width, water flow will be maximum. And if Ri is low, there will be some leakages, little. When Ri is very high, when Ri is very low, width is very high, resistance is very low, channel width will be very high. So when Ri is very low, what happens? You will have more losses. There will be more losses because water is flowing from this side to this way. So when Ri is very low, there will be losses, and when Ri is very high, there will be still losses, but may not be as good as the earlier case. But when Ri is equal to RL, maximum power will be transferred. So that is what the theorem says. But efficiency wise, the internal resistance of the circuit must be very high. Then only efficiency will be more. So that can be verified once you see. Once you work out it, you can verify that. Okay? Done.